Okay. So good afternoon, everyone. First of all, I'd like to thank the organizers for giving me an opportunity to present this talk and also rescheduling it because I was really unwell on Tuesday. So thank you very much for accommodating me. So today I'd like to present our first look at a potential correlation between high frequency SiO masons in AGB stars and mass loss rates. Now, this talk will be divided into four main sections, as you can see on the screen. And just a quick shameless advert that this is part of an overview of high frequency SiO masons in AGB stars that is going to be published, hopefully, within this year. And so stay tuned. Right, so just a very quick introduction about SiO masons, because I'm sure at this point of the conference, you've all heard of SiO masons already. And so, yeah, masons are, analogs of lasers, and they normally show very high intensity and compact in nature. And so they are very good for probing small scale structures in star-forming regions, extragalactic sources, and also evolved stars. Now, for silicon monoxide in particular, they are common in circumstellar envelopes, especially in oxygen-rich stars. And if we observe them, we can see, morphologies and physical conditions at the regions close to the stellar surface. So we're talking like smaller than 5 stellar radii. Now, in this talk, I'm going to be using two terms quite a lot. So the first one is low J. So J here is just, the rotational quantum number. And for low J, that's just, we're talking about SiO masons that are low waning frequencies. So those that are, like smaller than 100 gigahertz. And then we have high J, which correspond to high frequencies. These are usually greater than 200 gigahertz. And so just to keep that in mind. Now, in this work, we utilize the rich data set from the ATOMIUM Large Programme, which I'm sure at this point, again, you've heard already. And so these were observed with ALMA between 2018 and 2020. And these were observations in band 6, which covers 214 to 268 gigahertz. And this band, we've got a lot of SiO transitions that are really interesting because they are not really well studied, especially at this, resolution, spatial resolution. And so, we would like to take advantage of this data set and look at what the nature of these high J SiO transitions is. And so basically this presents a very good opportunity for us to find out whether there is any connection between where we see these high J SiO masons and mass loss rates in AGB stars. And also, if this correlation exists, it could really well inform us of an intrinsic link between like different mass loss processes and the physical conditions that are required for massive emission from SiO molecules. So let's move on to the methodology that we use. So when it comes to mass loss rates, I think we're all aware that we usually have a lot of large uncertainties associated with them. And these are usually quoted to be a factor of 3 to 10. And we would like to improve that in this study because, we are trying to find a correlation. And so we essentially compile a list of mass loss rates from the literature, and we calculated the weighted average for each source. Now, we focus mainly on CO mapping because we would like to make sure that we try to reduce as much systematic uncertainties as possible. And in this case that we don't have CO mapping, we decided to use some of the infrared measurements and models. But yeah, as we basically try to find as many CO map out there as possible. And then we decided to assign more statistical weight to more recent studies because we believe that these are more representative of the current state of the sources. And so we've got an updated table here with, so the uncertainties are shown in brackets. And as you can see, basically now we've got uncertainties that are down to something that is smaller than 60%, which is quite good for like a correlation search like this. Now, for the other variable that we have to find, that is, the flux-weighted angular separations of SiO masons, we essentially adopted sort of like, well, we adopted and adapted the method from Asaf et al. In 2011. And the idea here is we try to fit a 2D Gaussian to each clump of SiO mason emission. And these are, brighter than 5 sigma generally. And we call each Gaussian fit that we get a Mason component. And usually a Mason component map looks something like this. So we've got, so the X and Y here are dec and I offsets, and then the colors show the velocity with respect to the stellar systemic velocity. And so we've got a bunch of spots here, which are, these Gaussian fits. And then we calculated the flux-weighted mean radius encircling 90% of the total integrated flux, which is shown here as the red dash circle. And this is what we would like to know for each source and each transition in the ATOMIUM sample. And we also know the position of the star from the continuum and also the optical angular diameter, which is shown here in the black circle. And so we'd like to think of this, mean radius of SiO masons as multiples of this angular radius. Now, this is just to give you more examples of what we did with the ATOMIUM dataset. And you might notice that, this source, UDEL, is really interesting. Don't worry, we'll come back to this case later. So, yeah. Right, so time for the results. Now, here, I'm just going to show you some notes for the plots that I will show you in the following slides. So the Mason components that are shown, that are used in this analysis are from the 3 most common high-frequency lines from 28 SiOs. So, V equals 1, J 5 to 4, J 6 to 5, and then V equals 2, J 5 to 4. And in this analysis, we only include the sources that have got more than 10 fitted components. Now, the error bars that you will see in the plots after this, for the y-axis, it shows, the closest and the farthest Mason components in the maps. So not essentially an error, but this is more like a range of Mason components that you can see. And then in the mass loss rate, that's the standard errors of the weighted means. And in terms of the statistics involved, we'll talk about the Pearson correlation coefficients and also the linear regression models alongside with their coefficients of determination. So we've got our first result here for 28 SiO V equals 1, J 5 to 4. So we have 2 plots of flux-weighted mean angular separation in the unit of stellar radii against mass loss rate. So the one on the left is shown in linear scale, while the right shows the mass loss rate in log scale. And you can also see on the plot that we've got the correlation coefficient and the best fitted linear regression model. So as you can see here, for this particular transition, we got a correlation to be about 0.5, which is reasonable and pretty interesting already. And this trend seems to continue with the other 2 transitions as well. So if we look at the V equals 2, you can see that the correlation is even better in 0.71. And also the groups of sources that you can see here, you can basically see that for sources with lower mass loss rates, the SiO mesas are kind of clumped together at around 1, 2, 3 stellar radii, whereas we've got these two IRC sources, which are up here at around 4 to 5. Now for V equals 1J 6 to 5, again, we've got a pretty good correlation in 0.85 again, but this time, the range of angular separations are much larger at, up to about 8 stellar radii in the high mass loss stars. So far, that's very interesting. That's very good. We've got like a tentative strong correlation between these two parameters in the ATOMIUM SiO data. And we also saw from the regression model that mass loss rates actually account for most of the variation in the flux-weighted mean angular separations in two of the transitions. So V equals 1J 6 to 5 and V equals 2J 5 to 4. And also at a lesser extent in V equals 1J 5 to 4. Okay, so pretty exciting stuff, but there are some caveats that we have to discuss and improve before we can verify this finding. So firstly, we are not sure if it is actually physical, this correlation, because at the moment, we've got just one epoch of observations. And one might be tempted to say that, this correlation is intrinsic to high J SiO mesas because we haven't seen this in low J SiO mesas yet, as far as I know. Now, but the problem is, it is not uncommon to see sporadic and lopsided SiO emission in evolved stars like this, even for low J SiO mesas. So a good example of this is by Asaf et al. In 2011 in ARCAS. And as you can see, even though we expect to see sort of like a ring-like structure that I showed early in the presentation, it is still possible to see like very clumpy emission everywhere. So we think that, for high J SiO mesas, because they have got like higher upper state energies, we think that they might have to be closer to the stars. And that also means that we get more position uncertainty there. In the case of high mass loss rate stars, we might also see localized bumping like further out. So for example, in the IRC sources that we saw previously. Now, the next bit that is like really, really clear is the missing line of sight consideration. And because bright mesa components for high J SiO mesas, at least, they tend to be near the star, and that obviously causes underestimation of angular separation. So again, like coming back to this UDEL, we don't know whether this component here is close to the star, or is it just, it could be like very far away in the line of sight. But then again, at the moment, we have no idea. So it could be like very close, or it could be like out here, like, so that's a problem right now. We have to deal with this. So a couple of attempts have been made. So the first one is to do some deprojection. Now, the biggest challenge here is, geometric and depth considerations, because we have to assume a lot of things. So we have looked at using, aerial transform, for example. So essentially considering like concentric cylinders of, like linear combinations of well-behaved functions, and just consider the mesas as a bunch of rings that we can deproject. We have also looked at the possibility of adapting, like a model for elliptical galaxies for this, but again, we have to make a lot of assumptions in terms of densities and whatnot as well. So probably not ideal. Now, for modeling, we can assume, of course, that we get pulsations, and that means radial expansion in all directions, or even like some complex velocity profiles. But then again, we have shown already that there is a lot of asymmetry and localization in high-J SiO mesas. And so we've been working on a general 3D model of mesas, and yeah, the progress is ongoing, so we'll keep you updated. So I noticed that I've gone over time, so I'll just leave my summary slides here, and so thank you very much for your attention.
I have one about the location of these high-J SiO masers. Some of them seem to be located quite far from the star, not very close to the star, no, according to the spots you saw it in some on the maps. So they are originated far from the star or close to the star?
So you mean like from?
For example, in that one, they are located like at. Okay, no, I think I misunderstood the scale. It is in
Yeah,
R
so the
seconds.
scales here is
So that
very
corresponds to a few stellar radii or something like that?
yes.
So if you convert that to stellar radii, how is that?
So at the moment we have done so just as a preliminary result, we've got just optical angular diameter, but we also plan to use the uniform disk fit from the ATOMIUM data itself to make it more accurate. And so we use that as as the stellar radius that we use in terms of finding out the angular separations.
Okay,
Does that
but they
answer
are
your
like
question?
between 2, 3, 4 stellar radii. When you convert that to something like that.
Yes. So the
Okay,
majority of the components are between 2, 3, 4 stellar radii
okay,
in that sense.
okay.
Yep.
Thank you. Any other question? Yes, Marie.
Hi, Bank. Thanks for the nice talk. I was wondering on your plots where you showed the angular separation. So now I forgot, of course, that was on the y-axis in any case. Did you take the distance to the star into account as well, or is it just a projected angular separation?
So at the moment, it's the projected angular separations.
Also for your correlation plots then, or?
Yes.
Right.
And
okay.
so the problem right now is to account for the third dimension, right, in the line of sight. And I think we have explored a few possibilities, but so far I feel like to actually progress this work further, we would need multi-epoch observations to really constrain the third dimension that we are lacking right now.
All right, thank you.
This correlation you found between the mass loss rate and the separation of the SiO masers is also found for the low J SiO masers. So you found that for the high J, no?
Right. So I haven't done low J yet.
Yeah,
But
but
as
in the
far as
literature, I mean.
yeah, so as far as I know, there's no report on this. Yeah,
There's no
because you would
study on
need
that. Okay.
yeah. So I think this is something that is very interesting, whether we see this correlation or not in both low J and high J SiO
Okay,
mesons.
okay,
Yeah.
I see. Okay, thank you.